Welcome back to ECE 320A. We have a full agenda because we need to get a lot covered so that you are more than capable of solving all the homework problems, and those are due Sunday evening, and that's Chapter 11 material. There is an agreed upon time for the Exam 1 review. That was about 73% of the class, or those that voted, preferred this time of 6 to 7:30. I don't know that we'll go until 7:30. My blood sugar may be way down by that point. I will just be coming from another class, so I may be really down on Monday. That's at 6. I do not know where that will be. So watch for email or D2L on the news page for where that location will be. I hope we will get a room. If we do not, maybe it will be rescheduled to a different time. And I think the second time was on Tuesday at 4 o'clock. So depending on what we can obtain from classroom scheduling, I hope that that time works. Our exam is a week from today. And the process should be similar to what you have seen maybe on the practice exams. You will get one sheet of notes. That sheet is restricted to 8.5 inches by 11 inches, but you can use front and back. And that's for you to create. I'm not going to provide you with a sheet of notes. You create your own, and that will be essentially the process. You can use any calculator you want. You just can't use your neighbor or a computer or your phone. Okay? So it's going to be kind of hard. We're sort of tight in this room, but that's the process. We will start today getting our head out of the microwave, meaning I have another example, and it's from a current event of 120 degrees worth of separation between something. Oh, I can't wait. Has anyone seen these? These are in the state. They have just come online. They're a little bit west of Wilcox, about 15 miles west of Wilcox. There are 16 of those, and they stand 450 feet tall. So it's taller than any building in Tucson. It's taller than a 30-story building. And they almost produce, or their capacity for power, each one of those is about 2 megawatts. That's its capacity. So at full steam ahead, how many homes would that provide power for an average home? All right, we said so we have 13,500 is what they're saying, but that is for, not only does this have wind, but they also have 650 acres worth of solar panels that supplement this. So it is a renewable energy source for Tucson Electric Power, and that's where that 13,500 is coming from. They have 16 of these, I believe, and they say that the capacity on these 16 is about 30 megawatts. So I'm saying that each of these is a little less than 2 megawatts as far as what they can produce. And that's 2 times 10 to the 6th. And I said each home takes 1 times 10 to the 3rd. So now we add and subtract our exponents. How many homes would that have? About 2,000, right? All right, that's my current event, but those blades are how far apart, angle-wise? 120. Now, don't stick your head in the turbine either. That's one of the reasons, that was one of the objections to this is close to birds migrating between South America and Alaska. As engineers, we have to worry about all of these impacts. Social impacts, impacts on wildlife. You didn't think you were going to work and worry about birds, migration, but now you do. You may have to. All right, that's our current event. Now we need to speed up because I wanted to cover a lot. We will first talk about voltage current definitions, and I want to make it clear that what we mean by a phase voltage or a phase current depends on the context. It's not always the same. It depends on whether you have a Y connection or a delta connection, what you mean by a phase voltage. And I think that's what throws you a little bit. You're used to something meaning one thing, and here a phase voltage could be, it depends. It depends on the context or what you're working with. We will then pick up where we left off last time and essentially extract a single-phase equivalent from a three-phase YY circuit. We will look at how we transform between line to neutral and line to line voltages, and how we convert between line currents and currents in a delta load, which would be the phase current. We need to know how do we transition or how do we move back and forth, because sometimes what will you have access to in the real world? You may only have access to the terminals and the line. You maybe can't go into the neutral. And you may have to be worrying about all of this based on line voltage, which is line to line voltage, and line current, which is transmission line current. Big day. Then we'll talk about how do we compute those, or the total three-phase power, using line currents and line voltage. And we'll only use the magnitudes of those, but we somehow have to keep track of the angle between their phases, and that's going to be from the impedance. And that will enter by the cosine or the sine, depending on whether we're dealing with real power or reactive power. Then we can't finish today without a quiz. That will be our example, or one of the examples. We will talk about how to make these conversions. Maybe somebody now on the exam gives you a Y delta, and you go, well, I've only learned YY. Why? So now you have to figure out, how do I convert between Y delta to YY, delta Y to YY, or delta delta to YY, or do you just work with delta delta? And that's why it's important to know the ones above that. How do we convert between line voltage and phase voltage, line current and phase current? Then we will, if we have time, and we probably will not, I may have to add this later, impedance transformations for unbalanced, and maybe I'll just give you those notes at the end of these notes that we generate during today's class. The first thing that we are going to do, though, as promised, and this I'm going to really just quickly slide through, slide meaning scroll, are these definitions. Voltage and current definitions. We'll start with phase voltage, and that is defined to be the voltage drop, or the voltage across at the load impedance. Meaning, do you see that the phase voltage is not the same voltage in both cases? It depends on how the load is configured, and you don't just have one of these phases. I didn't draw the other three, but the other three are there. It's just in a Y-connected load, our phase voltage is the voltage across that phase's impedance. That's V sub AN, N again being Nevada, or the neutral. And in the delta load, our phase voltage is actually the line-to-line voltage. It's from terminal A to terminal B. That's the phase voltage. It depends on what interconnection you have, whether that's Y or delta connection. You're going to be upset when I scroll, aren't you? People are frantically trying to draw that, but you can get this later from the notes is what I'm hoping. No one's having trouble on D2L access, are you? Gaining access to the notes. Line voltage. That's the voltage dropped across two terminals of the line. And that's the same voltage, but in the Y connection, it's made up of two phase voltages. It's going to be V sub AN and V sub BN algebraically connected or computed based on KCL. But the line voltage is always between the terminals of the load. And a lot of times we just say line voltage when in fact you could expand that to say transmission line to transmission line voltage or line to line voltage. Maybe what's confusing could be is this is the A phase of the line to line voltage in the Y connected load. That's capital V sub AB. But do you see that those voltages are both measured? Just imagine you have a voltmeter and you're now connecting that voltmeter across two terminals. You're connecting it between the A and the B terminals in either the Y load or the delta load. So the load, well, I should say the phase voltage and the line voltage on the delta are the same. Did I say that correctly? The phase voltage in the delta is V sub AB. That's the voltage across that A phase impedance. That's also the line voltage. So your line voltage and phase voltage are equal in the delta load connection. They are not equal in a Y connection. Did that answer your question? And the reason it's not, I didn't want to label this because I didn't want you to be confused, but there's a voltage drop from A to neutral, and there's another voltage drop from B terminal to neutral, and we have to algebraically sum those appropriately to obtain that line voltage in the Y connected load. So phase and line voltage are the same in a delta connected load, and you can anticipate that that may be just the opposite when we start talking about currents. Here's the phase current. And again, I haven't drawn all the different terminals and impedances in this. I've just isolated on the A phase. But the phase current is defined as the current through a particular phase impedance, or if we were dealing with the source, we would be concerned with what current is going through the A phase generator or the B phase generator. Is what? So the question was, why are you labeling that I sub little a capital A? Because it doesn't, I don't even see a little a on that diagram. So I'm implicitly assuming that other part of this circuit is here, and that's the current flowing in the transmission line from little a to capital A. And where is that current here? And you're going to miss this if you're watching this video and not coming to class. That'll teach you. What's I sub AA here? It's right here, isn't it? But it then is made up of I sub CA and I sub AB. But I didn't want to put it on that diagram because I didn't want you getting confused what I'm trying to emphasize. This phase current in the delta is just the current going through that impedance in the A phase of the load. And all the others, when you get home, you can sketch this out in all its glory. You can put all of the different pieces together and you can label it, but you might want to emphasize the red as being those are our phase currents in these different loads. And I tried to then make it clear that this Y load, I sub little a capital A, is definitely not the same current as the phase current in the delta load. Wow, I got really big when I was making these notes. And here, for whatever reason, I included more. I guess I started getting a little bit aggressive with what I was sketching. But now this is the line current. The line current is the current flowing through a particular transmission line. And again, I haven't shown the little a, but the little a is on the generator side of this complete schematic. Those currents are the same current, but they're definitely not equal to the phase current, are they? In the delta load. But in the Y load, what do you know now? How are the line current and the phase current of the Y configuration, how are they related? Now you have to scroll back to the previous diagram and it should be exactly the same. What did we have the same with our voltages? Or what interconnection produced phase voltage equal to line voltage? That was the delta. Now what do we have? Now we have the phase current and the line current are the same in what configuration? The Y. It depends on the context what these phase currents and phase voltages are equal to. Yes?
So line voltage and line current are going to be the same, like big Y.
Yes, so the question was, in terminology or in terms, the line voltage is always going to be the same no matter what the load looks like. You're always going to be measuring that between the A terminal and the B terminal, no matter what the load, how it's configured. Likewise with the line current. It's always going through the A phase transmission line, the B phase transmission line, and that doesn't matter what the load, how it's connected. Is that what your question or comment was? And that's important because those are the quantities we can probably measure in a physical system. And so we actually may want to derive some formulas that only involve the line current magnitude, line voltage magnitude, and the angle between the voltage and current at the load. This, I hope, will make sense as we get through today's class. Other questions on those? Yes? The hats, I just thought about throwing a party, so I put some hats on these impedances. You know, I said I was getting a little bit aggressive with this diagram. So I was just trying to indicate that that A phase is not the same as the Z. And if it's balanced, they're different by a factor of 3. You can, the Z sub A hat would be 3 times what the Z sub A is, if it's a balanced, and we'll get to that later in today's class. I was just trying to make sure that you're not thinking that, oh, I can just make the conversion from Y connection to the delta connection by just rewiring it. No, you have to change the values of the impedances. They're not the same value. Single phase equivalent. Again, I'm going to scroll through this because I'm really anxious to get to the good stuff today. But because we already worked this from last lecture, and that's an F if you can't see it. Whoops. Now who knows what I've labeled? Oh, I put a negative sign somewhere. I better get rid of that. Oh. Okay, so this is single phase equivalent circuit extracted from a balanced three-phase YY circuit. And to obtain a balanced three-phase YY circuit, we needed all of our generator impedances to be the same. That's the Z sub little g, A, B, C. We needed the impedance in all three transmission lines to be the same. That's Z sub little a, or little LA, Z sub little LB, and Z sub little LC. And we needed all of the impedances in each of the phases at the load to be the same. We also needed a balanced set of sources of generator voltages. And what do we mean by that? How are the magnitudes of a balanced set of voltages, three-phase set of voltages, how are the magnitudes of those voltages related to one another? They're the same. And what are the angles of those voltages? 120, right? They differ by 120, and it depends on whether it's a positive phase sequence or a negative phase sequence, how B and C are related to A. Positive phase sequence is ABC, a negative phase sequence is ACB. Okay, draw that in a second. Here's your YY circuit from last time. Whew. Kind of makes your head sore, doesn't it? It's not too bad, though. All of these look about the same. It's just how they're interconnected. And these now, with all of the Z sub G's, the generator impedances equal, the VA, or the generator voltages, are now a balanced set of voltages. The line impedances are equal. The impedances at the load are equal. Now what I can do, and what did we learn last time? We learned that the current in the neutral conductor is what in a balanced system? It's zero, isn't it? If that's zero, then what's the voltage drop from Little Nevada to Big Nevada? Zero. There is no voltage drop. We can either put a short circuit or we can pull that wire. We're going to put a short circuit in there, forget Z naught, and just draw now a single, this you can sketch. This we didn't sketch last time. This is now the single phase equivalent circuit extracted from a three-phase balanced YY configuration. It has exactly the same load impedance as the three-phase. It has exactly the same transmission line impedance. It has exactly the same generator impedance, and it has the voltage at the source, and typically it's common to just extract the A phase. It's now the A phase voltage source. And now we have this neutral conductor with no impedance. And this you should just be whistling to solve this problem. How do you compute the line current? Just sum up the impedances and use those as what you divide into the source voltage. And there's your transmission line impedance. The only thing to keep in mind is now that we're in sinusoidal steady state, we need to make sure we're using phasors. We're keeping track of these complex quantities. Questions on that? Many times they may assume the generator impedance. They may say neglect the generator impedance. What does that mean? That means just short it out. It's zero. Maybe they say the transmission line impedance is negligible. Just put a short circuit from little a to capital A. Then finding the line current is no more different than what it was before. It's just we have a less involved total impedance. Questions on the single phase equivalent circuit? You've now learned how to extract information from chapter 11 and move back and work these problems using chapter 10 techniques. That's the idea. Once you know I sub a, little a, capital A, how would you find I sub little b, capital B? Because this might be what your boss asks. Getting some feedback. Not from the class, but from a speaker. What's capital I sub little b, big B, if I give you capital I sub little a, capital A? Did everybody hear that? I didn't very well. How is its magnitude related? They're the same. How is the phase? It depends on the phase sequence, doesn't it? You have to know, is this a positive phase sequence or a negative phase sequence? But once you're told that, then you know the B phase is either 120 behind or 120 ahead. Behind if it's a positive phase sequence, ABC, and ahead if it's an ACB. And now you know what the C phase looks like. Current, same magnitude, different phase. Questions on that? What you have to pay attention to is the following, and this is the note. The single phase equivalent line current, I sub little a, capital A, is exactly the same as the line current in the three-phase balanced circuit. But that's as far as you want to push that connection between the single phase equivalent and the three-phase. What I want to emphasize is the fact that you shouldn't be saying that I sub AA that's flowing in this neutral conductor in our single phase equivalent, that's not the same as the current flowing in the three-phase neutral. Because what did we already say about the current flowing in our three-phase neutral system? It was zero, wasn't it? Because we were summing the A, B, and C phases together. And all we're doing in this equivalent circuit is looking at one of those phases at a time. And that's why this isn't a hard concept. It's just keep things separate. When somebody might ask you and they say, well, if that's the current in the neutral conductor, then you've got current flowing in the neutral conductor in your three-phase circuit. Well, yeah, it's zero. Because A, B, and C are balanced, and they're combining to give you what we derived last time, which was I sub 0 bar being zero in a balanced circuit. That's the actual current in the neutral conductor of your three-phase circuit. Questions on that? Now I will slow down. What I want to do now is look at these voltage transformations. And by that I'm meaning, let's look at what happens when we have a Y-connected load. Because that's when the phase voltage and the line voltage are different. In a delta connected, they're the same. In this Y-connected load, what we want to do, or what we are trying to do, is we are relating V sub A in, which we will label as V sub phase or V sub phi, and we will just go ahead and let that be the reference phasor, to V sub AB. Here is our phase voltage in a Y-connected load, and this V sub AB is our line voltage. Let me now sketch what we have. We have the A phase impedance. We have the B phase impedance. And we have the C phase. Impedance. Here's the A terminal, B terminal, and C terminal. And now what I'm wanting to relate is this voltage V sub A n that's dropped from the A terminal down to neutral, and why don't I, apparently Dr. Marcelin was good with colors, and you know what I saw in today's comics? Not today's, but yesterday's. I'm a little slow in reading. I think it was Family Circle. Didn't have a 120 split on it, but it was a circle. And she said, "Mom, my favorite," what did she say? Supposed to not tell a joke or a story if I don't know the story or joke, right? But it was a little girl, and she said, "Mom, this is what I love to smell. A brand new box of crayons." Sorry, that was colors and multiple colors with Dr. Marcelin. So when I said colors, I just started smelling crayons. I don't even know what they said. It's been a while. All right, where was I? Red, VAB, is line to line or line voltage. Blue is our phase voltage in the A phase, but we also have this voltage capital V sub B in between the B terminal and the neutral. And we also have V sub C in, and we have all the other line voltages, V sub BC, V sub CA. I'm not going to even draw those. But if we do have this configuration, well, let me scroll down. What is KVL in this mesh that involves Z sub A and Z sub B? And let me start at the B terminal and go up to the A terminal. So now I want to measure that voltage across that gap. I entered the negative terminal first, so that's now minus V sub A B plus V sub A n minus V sub B n, And now I'm back where I started. The sum of those, Kirchhoff's voltage law says that those algebraically need to sum to 0. Is that equation okay? Are we okay with that equation? And that would hold. I haven't yet said anything about the sequence of these voltages, have I? Whether they're positive phase sequence or negative phase sequence, it doesn't matter. We would still label them the same, and we would still write the same KVL. But once we start to evaluate this, I then need to know how is V sub AN related to V sub BN. That will involve the sequence. Let's look at this now for the positive phase sequence, or for, oh, now I'm so nervous about colors, I don't know what color to use. Let's do the positive phase sequence, the ABC sequence. And now I'm going to say that V sub AN has a magnitude, and I'm going to try to be very careful and not overbar values or variables that aren't phasors. V sub phi is just a number. That's the magnitude of this phasor, V sub AN bar. And this has an angle. Let me use that as my reference angle. If I was really feeling generous, this could be an exam problem question. I like giving gifts on a week today. Okay. We'll all get crayons. So here we have VBN. What's that? Now, I bet some of you are going to go out and buy a set of crayons, aren't you? 64 or 128 colors. What's V sub BN's angle? That's minus 120. And I'm assuming these are all in RMS and the units are voltage. The RMS values allow me to use S equal VI star without that scaling of 1/2 in it. Yes, question? Yeah, so if you were at a yes, so if we had the negative phase sequence, the question was if we had ACB, which is the negative phase, then how would these last two? We could still use V sub AB as our or V sub AN as our reference. Then V sub BN and V sub CN would still keep the same magnitude. Their angles would just be different. V sub BN would now be at plus 120 because now as it's spinning counterclockwise past you, if you're standing in the first quadrant, you see the A phasor, then you see the C phasor, and then you see the B phasor, the ACB. You'll have minus 120 for the C and plus 120 for the B. Then you could use that in this KVL equation and continue to derive a slightly different result than what we are going to obtain. You would ask your kindergarten teacher, are we in ABCs or are we in ACB? And she's probably going to say, you're in ABC unless you're on Mars or something, right? No, you'll have to be told that. You'll have to be told you're in a positive phase sequence or a negative phase sequence. Or if you're not told, what do? Don't just sit there and guess or get frustrated. Just say, I'm assuming a positive phase sequence. Art forgot to include that information on the exam. So just write it down. I'm assuming this and continue. Then I know what you're doing. Wasn't what I was doing when I was creating the exam, right? Okay, let's keep going. Now what? We know what V sub AN and V sub BN. We're trying to derive what V sub AB is, the line-to-line voltage, in terms of V sub phi and 0 degrees. We want to know, how is this related to our reference phasor? How is its magnitude changed and how is its angle changed? That's what we're trying to derive. So we can solve this KVL equation for V sub AB. Just put it on the other side and put it back to the left. This is now V sub AN minus V sub BN. Or in terms of the actual phasors, this is a magnitude V sub phi at 0 minus the same magnitude, but now what's the angle? Minus 120. And we're subtracting that phasor. Now we simply have to do some complex math. We have V sub phi, we could factor that out if we wanted to, and we now have an angle of 0 minus an angle of minus 120. Those each have a magnitude of 1. So it's e to the j0 minus e to the minus j120, if you wanted to think about that, or you can just now apply Euler's formula. We can now say that we have V sub phi times what? Cosine of 0 plus j sine of 0. That's just 1, isn't it? Then we have minus cosine of minus 120 degrees, and I hope you're seeing these angles. Of course, you're seeing them this way, right? And this is now plus j sine of minus 120. And we have to keep track of the SIGNs as we go through this. This is now V sub phi, 1 minus, and if you sort of think about what the cosine of minus 120 is, that's minus 1/2. And what's the sine of minus 120? It's down, isn't it? It's now minus j square root of 3 over 2. So that now we have scaling V sub phi. We have 1/2 plus 1/2, or 3/2, plus j square root of 3 over 2. And that's the rectangular form of V sub AB, but we wanted to know, how does the magnitude change and how does the phase change? So let's convert that to polar form. We now have V sub phi. We can take the square root of real part squared plus imaginary part squared, and you're going to just plug it into your calculator. And this is now the angle that has the inverse tangent of square root of 3 over 3/2. I'm trying to show you where all these numbers are coming from. This is now 9 over 4 plus 3 over 4, which internal to that is now 12 over 4, which is 3. And so the square root of 3 is going to fall out as our scaling factor. And this is now the inverse tangent of 1 over the square root of 3, which is 30 degrees. And now we've related the A phase line voltage, V sub AB, to, this was actually V sub AN, wasn't it? I've sort of introduced a zero angle there, but now we've scaled that by the square root of 3 at 30 degrees. Meaning, if we had the A phase voltage in a Y-connected load, and somebody said, well, what's the magnitude of the line voltage at the terminals of the load? You could just scale it by a square root of 3 and you have it. If you need to know the angle, now you just change the angle by an additional 30 degrees. And sometimes it's nice to just have this in a sketch, so that now we could say here is V sub AN, and this is for a positive sequence, an ABC sequence. Where is V sub AB relative to that? How do the lengths compare? You just scale it by a square root of 3, 1.732. You just stretch V sub AN by that, and then how do you adjust its angle? It's now up 30 degrees from 0. This is now V sub AB. This is V sub phi at an angle of 0. This is now 30 degrees, and this is lengthwise square root of 3 V sub phi. Questions on that? And you can complete that with V sub Bn is now off at minus 120, and where is V sub Bc going to be? Maybe I should do that. This, if you are falling behind, this is actually figure 11.9a in your textbook, this phasor diagram. And this you could put on your sheet of notes. And it shows you the relationship between line-to-line voltage or line voltage and phase voltage in a Y-connected load. V sub A or V sub Bn is over here. Where is V sub Bc? "30 degrees ahead of that, which means that it's now down here, isn't it? It's 120 degrees behind V sub AB. Likewise, V sub Cn, these are all supposed to be the same length. And where is V sub Ca? 30 degrees ahead of that, right? And stretched by this square root of 3. So this is now V sub Ca. And that should be at plus 150 if the other one's at plus 120. Questions on that? The textbook will then have the other sequence, the ACB. The lengths still change by a square root of 3. The phases are just the opposite. Now you're minus 30 degrees relative to the A phase. I'm not going to sketch that. Let's look at the line currents, how those line currents differ from phase currents. What kind of a load do we need for that to be true? When are the line currents? Now I feel like I'm at Sesame Street. One of these things is not like the other. One of these things just doesn't belong. So the phase current and the line current, when do they not match? Y or delta? 50-50 chance. So now think of your delta And think of your Y. And how do your phase currents in the Y compare to your line currents? They're the same. Ding, 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 ding. So now we need to look at the delta load to compare how do the phase currents differ from the line currents in a delta configuration. We're now looking at how our line currents and phase currents related in a delta connection load. And if you don't get anything else out of this lecture, you can always get figure 13 in chapter 11. That will tell you this relationship. But if we sketched those, now we would have, let's say, a Z delta here, a Z delta here. And, oh boy. Let me call this A, B, and C. Here is the line current, that's a phasor. Here is our phase current in the A phase, I sub AB, and here is the phase current in the C phase. And if we wanted it, the B phase current in the delta load. We now want to perform a KCL at node A in order to relate the line current to the phase currents. And here we could say, well, let's just have the sum of the currents into the node A, that's I sub little a capital A, plus I sub capital C capital A, that must equal the currents leaving. So that now if I wanted I sub AA, that's now equal to I sub AB minus I sub CA. But these two currents are not the same. Which one's the line current and which one's the phase current? AA is the transmission line current, so that's the A phase line current. And I sub AB in the delta connected load is the A phase current. If I now have an ABC sequence, how do I, and maybe I use I sub AB now, my phase current as the reference. If I call this I sub phi at an angle of 0, what's I sub BC? That's a negative 120, isn't it? And this is a positive 120. if we now relate all of those, I'm not going to go through the algebra. Let me just write down the result. You know what to do because we just did it before. I sub AA is now I sub AB, which is I sub phi at 0 degrees, minus I sub CA, which is I sub phi at 120, positive. And if you work through that, you will end up with this being the square root of 3 at a minus 30 degrees times I sub phi at an angle of 0, where this is now the original A phase current, and the A phase line current is now bigger by a square root of 3, but it now lags the phase current in the A phase of the load. And again, you can sketch those phasor relationships. But I think you can start to picture these now, what the line current looks like relative to the A phase current. I want to now talk about how do we use these concepts to come up with formulas for the total complex power. And right now, let's look at the Y connected load. Say there's my A phase. B phase and C phase. I have now labeled, let me call my phase voltage in the Y connected load, V sub capital AN, here is the neutral conductor. Let me label that as having a magnitude V sub phi at an angle, let's say theta V sub A. And let me call this I sub AA. Let me say that has a magnitude of I sub phi. I'm not barring those, so those are just numbers at an angle of theta, whoops, I sub A. What have I indicated, or what variables have I only included in this diagram? The voltage is what kind of a voltage? Line voltage or phase voltage? Phase voltage. What's the current? Here you couldn't be wrong. You could say it's the line current or it's the phase current. They're the same, aren't they, in a Y-connected load? But now if I want to know what is this is a balanced load, I want to know what is a formula, an expression for the real power or the average power. They're the same, the real power or the average power in this one phase of this load. What's the formula for that? So now I'm going to look at different expressions for all of the different powers. And I now want to know what is the formula for the real and now I'm just saying per phase or per phi. What is P sub phi in terms of these variables that I've indicated here? What's the power formula? This is chapter 10. Okay, the complex power would be VI star, wouldn't it? That's the complex power, which includes real power and reactive power. I only want the real power right now. VI cosine of theta, where theta is the angle of the impedance, which is theta V minus theta I. Right? So the power, real power per phase, is just V sub phi, I sub phi, cosine, can I just say theta sub phi, where theta sub phi is actually theta V sub A minus theta I sub A. It's the impedance angle. This now means that you need to know the magnitude of the phase voltage, the magnitude of the line, or I'm sorry, the phase current, and the angle of the impedance of that particular phase. But now maybe all I have access to are line quantities, line voltage and line current. How is I sub phi related to I sub L in this configuration? They're equal, aren't they? So now I could rewrite P sub phi as I sub L cosine of theta sub phi. But how is V sub phi related to the magnitude of the line voltage in a Y-configured load? Do you remember that phasor diagram? How was the phase voltage that we had at 0 degrees related to its line voltage in length? The line voltage was a square root of 3 bigger, wasn't it? So if I want to express V sub phi in terms of the line voltage, how do I put V sub L into this formula? I'd need to just divide by the square root of 3. So now I have V sub line over the square root of 3. And now I could potentially give you this as just the power factor. That's the cosine of theta sub phi. Now you have per phase, in terms of line voltage and line current, a formula. And you just have to know those magnitudes. You do have to know the angle of the impedance, but that could come in the form of a power factor. If this is the real power per phase, what is the total real power? By total real power, I'm meaning for all 3 phases. That's the total. So power total, how is that related to P sub phi? How many phases do I have? This is going to get high-level math here. You have an A phase, a B phase, and a C phase. You have 3 phases. You just computed one of those, and they're all the same. You just have to scale it by 3. So this is now 3 times P sub phi. But P sub phi had a square root of 3 in the denominator. Now I have square root of 3, V line, I line, cosine theta sub phi. Could that formula get any easier? You need the line voltage, the line current, and the power factor, and you now have a way of computing the total real power of that 3-phase load. Square root of 3 VL IL cosine of phi, or cosine of theta. Yes? This is only for balanced, correct. So the question was, is this for balanced? And it's only for balanced conditions. That's what we're assuming when we did P sub T to be 3 P sub phi. We were assuming all three phases looked the same. What about the reactive power? Oh, if I go back, was it green? This was many days ago, wasn't it? But do you see this is exactly the same? It's just orthogonal to the real power. Instead of cosine, it's now sine. This now says that Q sub phi is V sub phi, I sub phi, sine of theta sub phi. But in terms of line quantities, that's V sub line over the square root of 3, I sub line, sine theta sub phi. That's per phase. And if I wanted the total reactive, Q sub T is now 3 Q sub phi, which is now this square root of 3 V line, I line, sine of theta sub phi. What am I going to want on exam 1? I may be needing the total complex power. But what do you know about the complex power? That's VI star. But now, based on what we've already derived, how would you maybe express S sub T? PT plus JQT, right? So here we have PT plus JQ sub T. And what was that? That was now effectively, we could write that in a little bit of an abbreviated form. That was the square root of 3 V sub L I sub L at an angle of theta sub phi, where that theta sub phi is cosine theta sub phi plus J sine theta sub phi. That's a shorthand. That's Euler's. So this is another way of writing this, is the total complex power is now square root of 3 V sub L I sub L, and those are just magnitudes. Those are just numbers. The magnitude of the line voltage, the magnitude of the line current. This is now cosine theta sub phi plus J sine theta sub phi. And that's actually a very powerful formula. You don't have to know a lot. All you have to do is go out and measure you just go out and measure the line voltage. You go out and measure the transmission line current. You know the power factor of your load. Now you can get the entire complex power from those measurements. Quiz. Here we go. And I hope you've already completed 3 or 4 modules of your speed reading class, because next week is our first exam, right? And it might be some word problems. So here, I need to start writing. If the line voltage, and you now need to read this very carefully. Okay, so line voltage, that's screaming at you, transmission line to transmission line voltage. If the line voltage in a balanced three-phase Y-connected load is 130 volts RMS, now you need to be told where you're measuring that line voltage at the load terminals. So now you're capital A and capital B, and you've measured that voltage, and it has a magnitude of 130 volts RMS. And the line current, that means the current in the transmission line, and the line current is 2 amps RMS. The question is, find the power factor of the load if the total three-phase inductive load consumes 120 watts. Go. You have a couple of minutes, and it shouldn't even take you that long, really. Is everyone getting an answer? What are some of the key words in this problem statement? Line voltage, that's V sub L, isn't it? Line current, that's I sub L. Total. Watts. Total watts means what variable? Capital P sub capital T, since it's total. Up here in blue, we had in black. We had a formula for P sub T. It was V line, I line, cosine of theta phi times the square root of 3. What were we told? We were told P sub T was what? 120? V sub L, 130. I sub L, 2. We know everything but cosine theta sub phi, but what's that? That's the power factor. Does everybody see? Power factor is the cosine of the angle of the impedance. That's cosine of theta sub phi. So if we use that, now in terms of our solution, P sub T is 120 watts, but that's equal to this square root of 3, V line, I line, and those are just numbers. Those are not phasors. Cosine of theta sub phi. But this is the power factor, and that's what we were wanting to solve for, and we have everything else we need. So we have power factor is equal to PT over square root of 3, V line, I line, 120, square root of 3, 130, and 2. What's the power factor? Is that what you got? What else? This is not it, is it? The other key word is inductive load, which means that what else do we need to include in this answer? Lagging. I really do think you have enough to finish your homework. Good luck. I will see you. Keep abreast of emails and D2L about the review session.